Welcome to video lecture of EE674 Modern Power Systems. The topic of this section is power electronic converters in modern power systems. In this video I will be discussing the example that we discussed. We will extend that little bit further, and I will discuss another example in this video. So in the earlier video we looked at buck converter for DC grid. So we calculated the inductance and output capacitance. So I will explain how we can develop a current controller for this converter. So in the theory we discuss how the model would be, and what would be the transfer function. So we will see how we can design a current controller for this buck converter. So we have a buck converter. So this is the input capacitor. We have the output capacitor, inductance, and if we take the internal resistance as Rp, we have the output current, and then we have the output voltage, input voltage, input current, inductor current. So this is the model. So we know that we can have the average model equation. So since we are looking at the inductor current control, we can take the corresponding equation. So since we have connected input source as the PV system, we won't be able to assume that the input voltage is constant. Therefore we have to go for the operating point model. So it will be LPD over dt, I inductance T, perturbation. We have the so this is the equation in a operating point model equation. Since this is a linear one, we can apply the Laplace transform. then we would have LPS inductance is going to be equals to D naught V in S minus, so this should be plus V in out DS RPI inductance S minus V out S. So we have this equation which we can use to control the current. So we can draw the block diagram. We have input DS, which has to be multiplied by V in operating point value, plus, then we have the D naught, and we have V in S, and also we have a feedback minus V out S. So this is the plant model. So we can look at LPSI inductances. So we have that as the output. We multiplied by 1 over LP 1 over S to get I inductance. In the right hand side we have D naught V in plus V in over DS. So that is what I have presented here, DS times V in operating point plus V in S times D naught. Then we have minus RPI inductance minus V out S. So these are the components. So now we can develop the controller. So first we can decouple the operating point value with the using the operating point value, which we will decouple. So when we do that, we will be moving into this point. So both of these two quantities we can consider as a disturbance on the system, and then we have the internal feedback RP. So what we can do in the controller is that we can use the RP hat, steady estimated RP value, and using that we can use the measured inductor current value, and this is going to be positive here because we have a negative feedback, so we can have a positive feedback. So that will decouple the RP, and then we can develop the controller. So we will assume that we are going to use a VI controller. So we have I inductances reference, and we get the measured value. It's the negative feedback. Then we have the proportional gain Kp, and we can have the integral gain, and that can be multiplied by 1 over S, and this is going to be plus. So assuming that estimations are perfect, we can have a simplified block diagram. So if we assume the estimations are perfect, then these will cancel out. So our simplified block diagram is going to be so in combination I will have one disturbance. We will mark it as disturbance S. We have 1 over LP 1 over S, and we have the high inductance S. So this would be the simplified block diagram. So we can get the command tracking transfer function, which is high inductance S divided by high inductance reference. So for this one we will assume the disturbance is 0. So our forward path function would be Kp plus Ki over S times 1 over LPS divided by 1 plus Kp plus Ki over S times 1 over LPS. So this we can write as KPS plus Ki over LPS. LP is S squared, and here we would have LPS squared plus KPS plus Ki over LP squared. So we would have KP S plus Ki over LP times squared KP over LPS plus Ki over LP. So this would be the transfer function. So we have a second order system here. So we can look at pole placement. So if we go for pole placement, can have S plus P1, S plus P2 is going to be equals to squared Kp over LP S plus Ki over LP. So from this we can write Kp as LP times P1 plus P2, and Ki can be written as LP times P1 times P2. So that's equal in the coefficients. So if we equal the coefficient for the S parameter, S term, so here we are going to have S squared plus P1 plus P2 S plus P1 P2. So P1 plus P2 is going to be Kp over LP. So from that we can write Kp is equals to LP times P1 P2, and P1 P2 is going to be equals to Ki over Lp, so we get KIO as Lp times P1 P2. So we have to find out what is P1 and P2, and thereby we have to find out what is Kp and Ki. For that, now in this system we have the highest frequency component is the switching frequency, which is 20 kilohertz. So this is 20 kilohertz, and we need to get the average current, inductor current. For that we have to have a filter, and we can have the filter cutoff frequency, let's say it is 10 kilohertz. So now this is the one which is going to determine what is our controller bandwidth. So we will take the two pole locations P1 as we will assume that, so we take the pole location plot. So we have on the frequency axis we have Fs, we have Fc, then Fp1 and Fp2. So this is 20 kilohertz, 20k, this is 10k. So I will select the Fp1 as 1/10 of Fc, and we will select Fp2 as Fp1 divided by 4. So this is kept in like this. So then I can write P1 as, so it is 1/10 means this is 1 kilohertz, this is 250 hertz. So P1 is going to be 25 times Fp1, so this is going to be 2005 radians per second, and P2 is going to be equals to 25 into Fp2, this is going to be 505. So now we can find out Kp as Lp times P1 plus P2. So Lp is going to be 154 times 10 to the minus 6, and P1 plus P2 we can write as 5 times 2000 plus 500. So this will give us Kp as 154 times e to the minus 6 times 5 times 2500. So this will give the proportional gain value as 1.21. Then we have the integral gain, which is Lp times P1 P2. So we have 154 10 to the minus 6. So P1 is 2005 and we have 505. So this is going to be 154 times e to the minus 6 times shift 5 squared 2000 times 500, and this is going to be 1520. So that's how we can find out the controller gain Kp and Ki. Now if you want, you can use the other controller design techniques available in classical control theories. You can look at rather than pole placement, you can look at the natural frequency and damping ratio. That's all. That is also you can use any other method that you would like to utilize. So that's how we can develop a controller for a boost converter. Now we will discuss another example based on a boost converter. So these are the specifications of the boost converter. Power rating is 5 kilowatt. Input is through a fuel cell of 72 volts. Output is 150 volts. Switching frequency is 16 kilohertz. Inductor current ripple is 30% of the average inductor current. Input and output voltages are 1% and 2% of the rated voltages. So you are asked to calculate LP, CP, ICP out. So let's work out this example. So we are looking at a boost converter. So initially we will assume that internal resistance of inductor is 0, Rp is 0, and converter is lossless. So we will assume that P in is equals to P out. So we will make those assumptions. So first we need to find out the capacitance and inductance. So initially we can look at the calculate the duty ratio. So we can write V out over V in is equals to 1 over 1 minus D, and we can write D as 1 minus V in over V out. So this is going to be equals to the output voltage, input voltage is 72, output voltage is 150. This will result the duty ratio as 0.52. So next we can consider the inductor voltage and current. So inductor voltage is going to be positive during the turn on time. So we have V in, otherwise we have V in minus V out. So this is the inductor voltage, and inductor current is going to be this. So this is the average value is going to be given by this. So that would be equals to the input current. So we can write I inductance average is going to be equals to I in. So first we can calculate what is the input, or this is going to be equals to P in over V in. So P in is 5000, input voltage is 72. So this results in current as 69.4 amperes. So from that we can find out what is the inductor current ripple. So that is going to be 0.3, 30% of 69.4. This is going to be equals to 20.8 amperes. So we calculate what is this. So we can write the inductor LP as V in times D over Fs times delta I inductor. So that is considering the turn on time. So using the same method that we discussed for the buck converter, you should be able to derive this equation. So V in is 72, duty ratio is 0.52, 16 times 10 to the power 3 times 20.8. So this will result in the inductance as 1.13 times 10 to the minus 4 Henry, and this would be equals to 113 micro Henry. To find out the input capacitance, we have to consider the input node. So we have the inductor current, which would be in this form. This is I inductance. Then we have the average current, which is I in. So we can consider the charge here, delta Q in. So we can express delta Q in as half ds by 2 times delta I inductance over 2, which will give us delta I inductance over 8 Fs. So we can write the Cp in as delta Q in over delta V in, voltage ripple in the input. So delta Q in we can write as delta I inductance over 8 Fs. Now this we can express as V in times delta V in over V in. So we can substitute the values. CPI is delta I inductance is 20.8 divided by 8 times frequency is 16 times 10 to the power 3, voltage is 72, and ripple is 0.1%, this is 0.01. So this will result in the input current, input capacitance to be 2.26 times 10 to the minus 4 farads, or 226 microfarads. So we get the input capacitance of the converter. Now this we can extend to find the output capacitance. So we can consider the output node. So the output diode, the diode current we can draw as like this. So this is the diode current, and we can have the input current I in. So we have the delta Q out. We can write delta Q out as I in times T on. We can write this as I in times D times Ts. So we have I in D over Fs. We can write Cpi as delta Cp out as delta Q out over delta V out, which would be I in times D over Fs times V out times delta V out over V out. So this will give us I in is so this should be actually I out, not I in. So we have I out here. So we need to calculate I out. So we can write this as P out over V out. So 5000 divided by 150. This will give the current as 33.3 amperes. So Cp out is going to be, I out is 33.3. Due to ratio is 0.52. Frequency is 16 kilohertz. Output voltage is 150. 2% is the ripple. So this will give us the answer as 3.61 10 to the minus 4 farads, or else we can write this as 361 microfarad. So that will give us the inductance and capacitance of the converter. Now let's try to develop a current controller for the boost converter as well. So for this one also, like we did for the buck converter, so you can look at the on state and off state equivalent circuit, so we can write the equations, then we can get the average model, and thereby we can get the operating point model as well. So I'm not going to go into the details of how we can obtain it, but I will write the equations. So the average model is going to be so you would be able to prove that the average model for this converter is LPD over dt I inductance T is equals to V in minus RP I inductive current minus 1 minus dt times V out T. So you can see this is going to be a non-linear one, so we can use the operating point model. So the operating point model would be LPD over dt I inductance T is going to be equals to V in T times RP I inductance T 1 minus T operating V out T, plus we would have V out operating and dt. So we can apply the Laplace transformation. So if we do that, we would get LP S I inductance S is going to be equals to V in S minus RP I inductance S. So this would be the operating point model in the S domain. So we can utilize that to develop the controller. we have V in S, we have the ds. So this is going to be the plant model. So we have V out ds minus, so V out ds minus rpi inductance minus 1 minus d naught V out. So that's the feedbacks, and we have the V in, which I presented here, and then we have the left hand side component. Now we can develop the controller. So we can take the estimate of the average this input voltage. So with that we can cancel out the effect of that. Then we can have the feedback decoupling, so we can have the rp hat, this is plus, and we can have the measured inductor current. Now we can have the controller I inductance reference, which is positive, and we have the measured, and in here we can have the controller GCS. So this would be the block diagram. We can again assume this as a disturbance. If we assume the estimations are perfect, then and also we will assume that GCS is a PI controller, so KP plus KI over S. So if we assume this as the model, then we can have the simplified one. We have the inductor current reference, so we have the KP, and we have the KI, and 1 over S. We have the disturbances, so similar to the earlier case, we can obtain the transfer function, command tracking transfer function. So if you solve this one, you can end up with the same equation, kps plus ki over lp squared plus kp over lps ki over lp. If we take the switching frequency is 16 kilohertz, so let's assume that our controller will take as 8 kilohertz, and I will take the pole location 1 as fc divided by 10 and fp2 as fp1 divided by 4. So this is going to be 800 hertz and this is going to be 200 hertz. Now similar to the earlier case, we will get kp as lp times p1 plus p2 and ki is lp times p1 and p2 assuming the pole placement. So p1 is going to be 1605 and p2 is going to be 405. So therefore kp is going to be, so lp value is 113 times 10 to the minus 6 times, so we need to get the addition, which is going to be 2005. Ki is going to be 1605 times 405. So when you solve this one, you will get the answers as 113 e to the minus 6 times 2005, which is going to be 0.71. And this is going to be 714. So that's how you can get the controller for the boost converter as well. So for the buck converter as well as the boost converter, once we have the inductor current, you can go for output voltage control or input voltage control as per the requirement. So I assume that this you can extend to the other level and you can develop a outer voltage controller or input voltage controller on your requirement. So those are a couple of examples on controller design and boost converter, simple design of boost converter and buck converter. So that would give you some background on controller design and calculation of converters for the basic DC to DC converters. The same method you can extend it for the other DC to DC converters as well. So with that we will conclude this recorded video, and thank you very much for your attention.